Good morning. Now today we will learn about bilinear transformation. In the last classes we have studied about the various methods of converting an analog filter to digital filter, which are the approximation of derivatives method, impulse invariance method, and now finally we are going to learn about bilinear transformation method. Okay. Now this is a definition. IR filter design using approximation of derivatives method and impulse invariant method are appropriate for the design of low pass filters and band pass filters whose resonant frequencies are low. These two methods we have studied. However, these methods are suitable only for the design of low pass filters and band pass filters with lower resonant frequencies. Now these techniques are not suitable for high pass or band reject filter. So in order to overcome this difficulty, we have found out a new mapping technique, and is called by the name bilinear transformation. Now this is actually a one-to-one mapping from S domain, that is from analog system, to Z domain, that is to digital system. That is, the bilinear transformation is a conformal mapping or one-to-one mapping that converts or that transforms the j omega axis, that is in the S plane, into unit circle in Z plane only once. This mapping is done only once, and that's why we call it as a one-to-one mapping. Okay, and this actually avoids aliasing of frequency components. Now this in S plane and as well as the unit circle in Z plane, etc., and I have shown in some of our earlier classes, so I am not explaining it right now. Now one peculiarity of this transformation is said here. In this case transformation, this actually results in a stable digital filter, as all the poles in the left halves of the S plane are mapped onto the points inside the unit circle of the Z domain. That is, I have already shown that suppose that this is the left half side of the S plane and this is the right half side of the S plane. All the poles of this left half of the S plane is completely mapped into the inside of the unit circle in Z plane. So by doing this type of mapping, it is the outcome is that we will get a stable digital filter. That is, in this by while mapping in this form, we will be able to get a stable digital filter from a stable analog filter. Now the bilinear transformation is obtained by using the trapezoidal formula for numerical integration. Now let us consider the system function or transfer function of the analog filter. Suppose that it is represented as HFS. HFS is actually the system function or transfer function of the analog system. It is represented as B by S plus A. Now the differential equation describing the analog filter can be obtained from equation 1 as shown below. That is, HFS equal to output Y of S by input X of S. It is again B by S plus A, this one. Now we are actually cross multiplying these terms, that is ys into s plus a and b into x plus s. So you will b into x of s, that is, so by cross multiplying s plus a into y of s and b into x of s, we will get equation 2. Now we are taking the inverse Laplace transform of equation 2, so this one will become d by dt of y, and this will become a is constant. So inverse Laplace transform of y of s is y of t, b is kept as such. Now the inverse Laplace transform of x of s is x of t. So equation 3 you got. Now we are just applying the limit on both the LHS as well as RHS of equation 3 by taking the constants a and b outside, and the limit of integration is from nt minus t to nt. Just we are applying the limit, so you will get equation 4. Now we have a trapezoidal rule. Suppose that you have a constant a of t dt, you are integrating between the limits nt minus t to t, then the formula is like this. Now we are applying this trapezoidal rule or formula to each of these terms in equation 4 so as to get this one. Okay, so we are applying this one. How it will look like? Y of nt minus y of nt minus t. Now the second term, how it will look like? A is a constant, it's taken outside. As per the formula, you have a t by t, so t by t is written here. Then what will be this? Y of nt minus y of nt minus t. This is again written as such. Now by applying this formula to each of these terms in equation 4, we will reach this particular equation, and I have worked it out, and it is very easy to obtain that equation. Okay, so you also please work out. Now we are going to take the Z transform, or till now we were talking about analog system, that is transfer system or system function or transfer function HFS. Now we are going to speak about the digital system or Z domain. So h of s will be now become h of z, y of s will become y of z, and x of s will become x of z. So you have a formula like this, that is h of s, what was it, b by s plus a. Now b is kept as such. Now in place of es you have got 2 by t into 1 minus z raised to minus 1 by 1 plus z raised to minus 1. Now this was equation 1, right? Now just compare equation 1 and equation 6. This is equation 6. So in both these equations that we are comparing, h of s to h of z. So RHS b is common as well as a is common. You are only left with s. What is s? 2 by t. On comparing equations 1 and 6, you will get s as 2 by t into 1 minus z raised to minus 1 by 1 plus z raised to minus 1. Now dividing this numerator and denominator with z, you will reach at this particular equation, that is s is equal to 2 by 2 into z minus 1 by z plus 1. Now, as already seen in impulse invariance technique, the general characteristics of mapping z equal to e raised to st can be obtained by substituting s is equal to sigma plus j omega and expressing the complex variable z in its polar form. What is it? R e raised to j omega in equation 7. See, this is your equation 7. Now, what you are doing is, you are just replacing this z with its polar form. What is it? R e raised to j omega. So, you will get this. Now, how you get this particular step? You are multiplying both the numerator and denominator with r e raised to j omega minus 1. Then you will reach at this particular equation. Now see, this is actually sigma plus I j omega. Okay, I j omega. That is, this particular equation is of the form 2 by t into sigma, that is sigma plus I j omega. Here in place of sigma, this is a term, so you write like this. Now in place of omega, you have got this particular term, so you write this. Okay, so see, this omega and omega, both of them are angular frequencies. This is angular frequency in analog system and this is angular frequency in digital system. Okay, so this is of the form, and you have written this sigma and omega separately. Now from equation 9, it can be seen that if r is less than 1, then sigma is less than 0, and if the reverse occurs, that is if r is greater than 1, then sigma is greater than 0. Thus, the left half of S-plane, that is the left half of S-plane, as I already said, is completely mapped onto the points in the inside of the unit circle in Z-plane, and as a result, what we get, that after the transformation, what we get will be a stable digital system. Okay, this I have already mentioned. Now consider equation 10. Suppose that r is equal to 1. We are taking its magnitude as unity. Then sigma is 0. In that case, what will happen to equation 10? Omega will become 2 by 2 into sine omega by 1 plus cos omega. Now how this reduces to this? See, you know, sine 2 theta is equal to 2 sine theta cos theta. So sine 2 omega will be 2 sine omega cos omega, right? So what will be sine omega? It will be 2 sine omega by 2 cos omega by 2. So that is the numerator. Now what about the denominator? You know that 1 plus cos theta is equal to 2 cos square theta by 2. So what will be 1 plus cos omega? It will be 2 cos square omega by 2. That is the numerator. That is the denominator. See, 2 cos square omega by 2. So in order to reach this particular form, they are just adding and subtracting a term like sine square omega by 2. Otherwise, you are left with only 2 cos square omega by 2 in the denominator as per the formula of 1 plus cos omega. Okay, so omega will now reduce to 2 by 2 tan omega by 2, or omega will be 2 tan inverse omega t by 2. Now equation 12 actually gives, as I already said, it is a relationship between the frequencies in the two domains, that is in S domain and Z domain. That is omega angular frequency in analog system, this omega angular frequency in digital system or Z domain. Okay, that is omega is actually the angular frequency in analog system, that is in S domain. This is actually the angular frequency in digital system or Z domain. Now it is seen that, or it can be noted that the entire range in omega is mapped only once into the range omega less than or equal to minus 1 plus minus pi plus pi. However, as seen in figure, we can see that this mapping is non-linear. Why? Because After mapping from analog system to digital system, that is from S domain to Z domain, all the lower frequencies are expanded, whereas all the higher frequencies are compressed or contracted. Okay, now this is mainly due to non-linearity of the arctangent function, and this phenomenon is called frequency warping. So in order to in order to support your explanation, I think you can draw this particular figure, no need of drawing the other two figures. Okay, now this is just an example. When you are studying this problem, you can just go through. Here the system function or transfer function of analog system h of s is given, and you have to find the transfer function, that is h of z, in the digital system. That's your aim. So here for that you have a formula. This formula you have to study. Omega r, resonant frequency, is given in the question as pi by 4. Now also sampling period you have to find out. There is a formula for this. Okay, so you will get the sampling period, and from this you have to find this omega c, and finally this is a formula for h of z, that is h of s at s equal to 2 by 2 z minus 1 by z plus 1. This is a formula, and finally you can substitute the value of t here. T is obtained here. So and this we'll get the transfer function in the digital system. You can just go through this problem. Okay, no need of studying this. I just for your information I have given, you can just go through it. Okay, but this the theory of this one is very important. That is all these four slides, the definition, then the explanation of the mathematical expressions and all. Compared to the other two methods, I think bilinear transformation is the most important one, and it's also very easy to study. So these questions are very important. That is how to convert or explain the methods for converting an analog system to digital system. I mean how discuss in detail the various methods of designing IR filter from analog filter. Which are the three methods? Approximation of derivatives methods, impulse invariance method, and finally bilinear transformation. So these three methods you have to study it very well for your exam point of view. Okay, that's all for now. Thank you.